So class is recorded now. And Darius, Andrili, Hall, Jay, Ikara, and Raul, like the presenter. So whoever is ready, please go.
Can you see my screen?
Yes, Jay.
This is 5.18. Suppose that X is a normally distributed random variable with mean mu and variance sigma squared. If P of when X less than 10 equal to 0.6700 and P of X less than 20 is equal to 0.9750, approximate mu and sigma squared. So we just plug into the formula. In the formula, we have P of X less than A is equal to A minus mu over sigma. So in this case, for the first case, we have X less than 10. So instead of X, we got 10. So we have this one. Phi of 10 minus mu over sigma is equal to 0.6067. That's the given. And we use this table to convert the number. So we got is equal to is equal to phi of 0.44. So we just set our equation. So we got 10 minus mu over sigma equal to 0.44. We multiply the sigma. We got the first equation. And similarly, for the second part, when X is less than 20, we got phi of 20 minus mu over sigma equal to 1.96. We got the second equation, and we do some elimination. We got sigma equal to 125 over 19, mu equal to 135 over 19, and we're looking for sigma squared, so we square this term, and we got this final result.
Great. Very clear, direct. Thank you, Jay.
Thank you.
Okay, that's a 39.
Okay,
Yeah.
hello?
Hello, Darius. Yeah,
Yes.
go ahead.
Okay, so 5.39, if y is uniformly distributed over 0, 5, what is the probability that the roots of the equation 4x squared plus 4xy plus y plus 2 to 0 are both real? So we have to first get the discriminant. The discriminant has to be greater than or equal to 0 for both for the reals to exist. So we just take the equation, plug in the values. We get 16 times y plus 1 times y minus 2. So now we have to satisfy that discriminant greater than or equal to 0. So then we look at the cases. So there's two cases, but because y is uniformly distributed over 0, 5, we choose y greater than or equal to 2, and then plug that in to calculate the probability, which is 3/5.
Nice. Nice. First look, I was thinking, okay, what is this question? Great. Thank you, Darius. If anyone has any question, feel free to jump in. All right, who's next?
I can go next. Hi.
Okay.
I'm doing 5.27.
Okay.
It says in 10,000 independent tosses of a coin, the coin landed on heads 5,800 times. Is it reasonable to assume that the coin is not fair? The x be a random variable. X is the number of times the coin landed on heads, which is 5,800 times, 5,800. N is the number of times, the number of tosses, which is 10,000, and the probability of heads or tails is half or 0.5. So P and Q equals 0.5. The expected value would be 5,000, and the variance would be n by p by q, which is 2,500. The standard deviation is the square root of the variance, which is 50, and sorry.
Oh, it's gone. Okay, coming
Sorry.
back.
The standard deviation is the square root of the variance, which is 50, and the mean or expectation is 5,000. Since the coin landed 5,800 times, that's 800 more times than the expectation or the mean. So we divide the standard deviation, we divide the 800 by the standard deviation, and that gives us 16. And 16 is a lot of deviations from the mean, which means that the coin is biased and not fair.
I see. I see. Nice. Thank you.
Bro.
Right. Next one.
Hello.
Hello.
Hi,
Wow.
I'm going to do question 19, chapter 5. Let x be an exponentially distributed random variable with mean half. Find the value of c when the probability of c or greater is 0.25. So the probability density function for this exponentially distributed random variable is lambda e to the negative lambda x for positive x. And it's given us the mean as half, but the mean is the expected value, which is 1 over lambda, so lambda would be equal to 2. So now we have the distribution function for when x is greater than c as 2e to the negative 2x from c to infinity, or the integral from c to infinity equals 0.25. And that simplifies to, the integral of that is negative e to the negative 2x, and that simplifies to negative e to the infinity plus e to the negative 2c, which is 0. The first part of that is 0, so it's just 0 plus e to the negative 2c is 0.25. If you ln both sides, that's negative 2c equals ln of 0.25. Divide both sides by negative 2, and you have negative ln of 0.25 over 2, or ln of 4 over 2.
Okay, can you simplify our n4 over 2?
Yeah, it's ln to, it's ln2, right? Oh.
Yes.
Because I got the first part. The book said the answer was the third part. I'm like, oh, okay. I didn't. Yeah, it's ln2.
It's okay.
Yeah.
Yeah. Yes. Okay. Thank you, Raw.
Thank you.
All right. Next one. We have Hao, Ikara.
Hello, Professor.
Hello. Good evening.
I'm going next.
Okay.
So can you see my screen?
Yes, it's popping up. Yes.
Okay, I'm going to present question number 24. The lifetimes of interactive computer chips produced by a certain semiconductor manufacturer are normally distributed with parameters mu is equal to 1.4 multiplied 10 raised to power 6 hours and sigma is equal to 3 multiplied 10 raised to power 5 hours. What is the approximate probability that a batch of 100 chips will contain at least 20 whose lifetimes are less than 1.8 multiplied 10 to the raised to the power of 6? Let x denote the lifetime of an interactive computer chip. Probability, which we have to find x less than 1 equal to 1.8 multiplied 10 raised to the power 6 is equal to probability into z less than equal to 1.8 multiplied 10 to raised to the power 6 minus 1.4 multiply 10 to the raised to the power 6 over 3 multiply 10 to the raised to the power of 5. These values are given in the question. After calculation, we will get that z less than equal to 1.333, and after getting the value from the z table, we will get that 0.9082. Now we want that 20 or more out of 100 should have lifetime less than 1.8 multiply 10 to the raised to the power 6, which is in the basically we have to find. So from the question we will get that probability we have which we have find and total number of chips which are 100. Mu is equal to n multiply p, and after multiply we will get 90.82. Then sigma is equal to npq under root. After putting the value, we have all the values. Then after putting the value, we will get 2.89. Then we have to find y greater than equal to 20 is equal to probability into z, and greater than equal to which we have find the value of mu over and then we have to find the value of sigma, then putting all in the formula, and then we will get minus 24.505, and which is the value when we see in the table of z, we will get that it's approximately equal to 1.
Wow, 100%.
Yeah.
Okay, great. Nice job.
Thank you, Professor.
Thank you. All right, we're left with Hao and Xiu Yu.
Question number 5.20. In a study, 55% of population is in favor of constructing a new shopping center. If a random sample of 400 people is selected, find the probability that A, at least 200 support the construction of the new shopping center. B, people between 250 and 350 support the construction of the new shopping center. C, at most 225 support the construction of the new shopping center. We know that 55% of the population is in favor of construction. Then we know that there's like 45% is not in favor, and we can find mu by just 400 times 55% to get 220, and then sigma just by the formula. And for A, it's like at least it's equal to a greater than or equal to 200. It's seem to use this one, which is x greater than 199.5. Plug into the formula, which like Jill had like said in the previous, to find that it's minus 2.06, and find it by the z-score tables, and then you want minus the total to get like 0.9803, or like using the z-score table. You can also find this number. And for B, you will do the same thing for 250 x and 350, between 250 and 350, and then plug into the formula for and find the z-scores of 3.06532 and 13, then subtract them to get the 13 will be like 1, and this is a z-score for this one to get 0.001. And then for C, you're finding like at most 225. Just do the same thing as the previous one, and then find the z-scores of 0.55 to get 0.6 70979.
Okay, great. How do you know this is a normal distribution though? Because I don't find it in the question.
Just kind of guess like
I
which
see.
like
It's like,
distribution will be used.
okay. All right. All right. Thank you, Hao. Okay, Xiu Yu is the last one.
Okay. Can you see my screen?
Yes.
So I'm going to present 5.21. The weight of a group of people is independently and normally distributed, with mean 70 kg and standard deviation 4 kg. What percentage of individuals from this group weigh less than 75 kg? What percentage of individuals from this group weigh more than 67 kg? So in this question, we use the normal random variable, which is the probability of x less than equal to a, which is equal to the phi of a minus mu over sigma, and z is equal to x minus mu over sigma. So x in here is represent the number of weight. So the mu, which is the mean, is equal to 70. And the sigma is equal to 4. So the probability of x less than 75, which is equal to the probability of x minus 70 over 4 less than 75 minus 70 over 4, which is equal to the probability of z less than 5 over 4, and is equal to phi 1.25. And by the table, we know that 1.25 is equal to 0.8944. So the answer is 89.44%. So then the probability of more than 67 kg. So I first calculate the probability of less than 67 kg, which is equal to the probability of x minus 70 over 4 less than 67 minus 70 over 4, which is equal to probability of z less than negative 3 over 4, and is equal to phi of negative 0.75. And by the formula that the phi of negative x is equal to 1 minus phi x. So it's equal to 1 minus the phi of 0.75, which from the table is equal to 0.7734. So it's equal to 0.2266, and find the probability of x more than 67, which is equal to 1 minus the probability of x less than 67. So it's equal to 0.7734.
Great.
Mm.
Great. All right. Nice. Normal distribution is very useful. Something called the limit theorem. Limit. I forgot the name. So yeah. Okay. Great. Thank you.
You're welcome.
All right. Anyone else like to present? All right. Tomorrow is exciting day. Tomorrow starts our spring break. Okay. I need to grade your papers during the spring break. So today we're going to finish chapter 5. When we come back, we're going to start a new chapter. So a couple more things to talk about, I think. Yeah, gamma Cauchy, and beta. So let's go to gamma distribution. We don't need to memorize. The density function because it's really difficult. But we need to understand the variables and in what kind of situations we want to apply the distribution. So let's see this one. Gamma distribution. A random variable is said to have a gamma distribution with parameters, two parameters, alpha and lambda, with lambda positive, alpha positive, if its density function is given by so. Lambda e to the negative number x. So we see this part is exponential one, and then multiply by lambda x times raised by alpha minus 1. And if x is non-negative, if it's it'll be 0 if x is a negative. So this gamma of alpha called a gamma function. So this is divided by gamma of alpha. And is defined as gamma of alpha equals the integration from 0 to positive infinity e to the negative y. So we have to check what is y, and y raised by alpha minus 1 dy. Okay, y is just a variable. Okay, so cutting along the axis, y-axis, okay, we have this. So this is how gamma alpha defined. Integration of gamma of alpha by parts, we get this. Alpha minus 1 times gamma takes alpha minus 1 as input. For integral values of alpha, say alpha equals to n, we have gamma of n, apply the formula, right? Would be n minus 1, gamma takes n minus 1 as input. And that would be n minus 1 times n minus 2, gamma of n minus 2, so on and so forth. So in that case, we get n minus 1, n minus 2, up to gamma 1. 3 times 2 times gamma of 1. And since gamma of 1 equals to, if we plug into this, right, we get gamma of 1 equals 1. So gamma of n, but the n has to be what do you call it? Natural numbers, right? For integral values of n. Integral values, so integrable, but basically we can think as natural numbers. So gamma of n equals to n minus 1 factorial. Interesting. Yeah. Okay, when alpha is a positive integer, say alpha equals n, the gamma distribution with parameters alpha, lambda often arises. In practice, as a distribution of the amount of time one has to wait until a total of n events has occurred. More specifically, if events are occurring randomly and in accordance with the 3 axioms of section 4.7, then it turns out that the amount of time one has to wait until a total of n events has occurred will be a gamma random variable with parameters of n and lambda. To prove this, let Tn denote the time at which the nth event occurs, and note that the Tn is less than or equal to T if and only if the number of events that have occurred by time T is at least n. That's when n of T equal to number of events in the interval from 0 to T. Three axioms in section 4.7 is the probability axioms. So this is a little calculation here. Well, the final identity follows because the number of events in this has a Poisson distribution with lambda t. Differentiation of the preceding yields the density function of Tn. Okay, we don't need to go over that. So we need to know this. Hence, Tn has a gamma distribution with parameters n lambda. This distribution is often referred to in the literature as n long distribution. So when n equals 1, the distribution reduced to exponential distribution. The gamma distribution with lambda equals half and alpha equals n over 2, and the positive integer is called chi squared distribution with n degree of freedom. The chi-square distribution often arises in practice as the distribution of area involved. Okay, we don't need to know that. Let's see example. What kind of example we need? Oh, again, right, with the distribution, we want to know expected value or its mean and its variance. So let x be a gamma random variable with parameter alpha and lambda. Expected value, so calculated, that's a 1 over, because this gamma of alpha, we can put outside integration. We want to integrate with x and lambda. So we have this lambda. We have this lambda raised by alpha minus 1. Oh, this is saying, okay, let's multiply alpha over lambda over lambda. So we have a 1 over lambda outside. We have this lambda. And also we have this x. So lambda x becomes lambda x alpha minus 1 becomes lambda x alpha now. And rewrite this. So in the end, we have this. So integrate this. We get this. We get a gamma alpha plus 1 over lambda gamma alpha. Periodic. So that equals alpha over lambda. Equals alpha over lambda. Because we have this gamma of alpha divided by gamma of alpha minus 1, that equals alpha minus 1. So similarly, we have this gamma alpha plus 1 divided by gamma alpha, that equals alpha. So alpha over lambda. So that's the expected value. Interesting, isn't it? This is a gamma distribution. So it takes two parameters, alpha and lambda. And its expected value is alpha over lambda. Then we calculated the variance. So it skipped, but basically it's alpha over lambda squared. So that's for gamma distribution. We're going to skip, oops, what did I do? We're going to skip Weibull distribution. Let's go to Cauchy distribution. Cauchy distribution, the density function is given by this, and x can be negative, right? So this is a special one. Cauchy, the random variable can be negative. So goes from negative infinity up to positive infinity. 1 over pi times 1 over 1 plus x minus theta squared. Let's see this example. Suppose a narrow beam flashlight is spun around its center. So that's this, spin around its center, which is located a unit distance from the x-axis. Consider the point x at which the beam intersects the x-axis when the flashlight has stopped spinning. If the beam is not pointing towards x-axis, repeat the experiment. As indicated, the point x is determined by the angle theta between the flashlight and the y-axis, which from the physical situation appears to be uniformly distributed between negative pi over 2 and pi over 2. The distribution function of x is thus given by the cumulative probability tangent theta, so x depends on theta because this is 1. So tangent theta less than or equal to x. So tangent theta equals opposite over adjacent equals x over 1. Basically it's x, so tangent theta. Then that means same thing means the theta is less than or equal to arctangent of x. Did you correct? Did you correct? Someone is asking me a question. Did you correct homework 4 yet? What do you mean, Angeli? I mean grade homework 4 yet? What do you mean by correcting homework 4?
Grading, yes.
I'm sorry, expiration date?
I was asking if you graded homework 4 as yet. Sorry.
Oh, okay, not yet. I'm sorry. Not
Okay.
yet. Yeah. Yeah, I'm piling up a lot of things to do during the spring break. Okay, that's the probability of a theta less than or equal to arctangent of x, and which is given which is given by the distribution density function at half plus 1 over pi arctangent of x. What does this give us? Where the last equality follows since theta being uniformly over negative pi over 2 to pi over 2 has a distribution. Theta is less than or equal to a is a minus negative pi over 2 divided by pi, which is half plus a over pi. Then the density function x is given by differentiate the cumulative probability function, which is we get 1 over pi plus pi times 1 plus x squared. And then we see that x has a Cauchy distribution. Okay, anyway, so let's see, what do we know? What do we want to know about Cauchy distribution? I don't really know. Let's see what kind of homework you can pick. So that's Cauchy distribution. Lastly, beta distribution. A random variable is said to have a beta distribution if its density is given by, anyway, so, you always get credits, even you submit your homework late, all right? So if you submit your homework late, you still get credits. Just you don't get 100% credits. Beta distribution. A random variable is said to have a beta distribution if its density fits into this situation. X goes from, so the random variable goes from 0 to 1 interval. 1 over b takes AB as input, x raised by a minus 1, 1 minus x raised by b minus 1. And how is b defined? B is defined as x goes from 0 to 1, x raised by a minus 1, and 1 minus x raised by b minus 1. The beta distribution can be used to model a random phenomenon whose set of possible values is some finite interval from C to D, which by letting C denote the origin and take D minus C as a unit measurement can be transformed into the interval 0 to 1. When A equals B, the beta density is symmetric, about half. Let's see. Catherine, for my case, I didn't know that my homework 4 wasn't submitted. I thought Blackboard did because I remember doing it, so I won't get 100% if I resubmit it late. Catherine, what's your question? You submitted, let me see, let me check. So needs grading. midterm. Oh, I see. So I have here house homework, Emma's homework, I read homework, and Kara's homework. Catherine, I don't see your homework. Yeah, I only have 4 people's homework showing up. Unless if you submitted earlier, you get grades already. Because I know some of you the homework 4. Some of you submitted early, homework 4. Yeah, some people. Jie submitted already. Shou Yu submitted already. Yingping submitted already. Already got grades. They submitted early, right? If you haven't submitted, just submit. You always get credit. Okay, so Catherine is saying you submitted, but the Blackboard just didn't record that. That's interesting. I think someone else told me the same thing. Just resubmit, okay? Resubmit. I'll consider this situation. It's not your fault. Okay, let's see. So when A equals to B, the beta density is symmetric about half. And given more and more weight to regions about half as the common value A increases, when A equals B equals 1, the beta distribution reduces to the uniform from 0 to 1. Right? If it's 1, this is x raised by 0, this is raised by 0, this is a 1 dx that becomes uniform. When B greater than A, the density is skewed to the left. When A is greater than B, it's skewed to the right. The relationship beta of A and B equals to gamma of A, gamma of B divided by gamma of A plus B. So this can be shown by beta of AB equals to this, and the gamma function. Yeah, beta function, gamma function used a lot in number theory. When I was doing my PhD, I did it with topology and differential manifolds. So I never used this, but I see my colleagues, they use beta function, gamma function, Cauchy, function all the time. Anyway, we don't really need to know this. All right, unless you are interested. This is beyond our course. Just to know the name, all right? Because they didn't calculate the expected value. Oh, this one did. Okay, beta has, but gamma function didn't have, and the Cauchy didn't have. Oh, gamma has. Gamma has alpha divided by lambda, and the variance is alpha divided by lambda squared. Cauchy doesn't, but beta has it. Let's see betas. Betas expected value is A divided by A plus B. Nice. Variance, or variance AB divided by A plus B squared times A plus B plus 1. These things are interesting, all right? Mathematics is crazy. I know some of you are doing mathematics. Hopefully in the future you choose one field to dig deep into it. Mathematics can make you crazy and also can be very enjoyable because there's so much, interrelationship is very, very interesting. Anyway, and I think that's it. For these distributions is beyond our course. So just to know the distribution, just to know the name, all right. To know maybe some situations can be applied to, and to know its expected value and the variance formula, if they have them, I think that's good enough. So when we come back, let's see how much left we have to do. So that finishes chapter 5. So chapter 5 mainly is about uniform random variable, normal random variable, super important. Because one of the theorem, central limit theorem, okay, finally I remembered. the probabilities, statistics are very closely related. So statistics build upon two theorems. One theorem is called the central limit theorem. Central limit theorem says, doesn't matter what kind of probability distribution you have. If certain criterion is satisfied, you can always use normal distribution to approximate. So that's why normal distribution is very super important in life. We stopped at a Pareto distribution. Is Pareto distribution on our syllabus? I don't want to even talk about those difficult distributions. I'm checking our syllabus. Yeah, we don't need to talk about the Pareto. So for chapter 5, uniform random variable, which is not difficult at all, right? Exponential random variable and the density function can be memorized. A normal random variable, normal distribution is the most important one. All right. Again, the central limit theorem guarantees. Central limit theorem says, we don't have to worry about so many kinds of probability density functions or distributions. Some very easy to be satisfied condition, if there are some very easy condition to be satisfied, we can always use normal distribution to approximate. So the most important material for this chapter is normal distribution, is normal random variable, all right? Then gamma, beta, Cauchy, know the name, know the expected value, get familiar with the density function, and right, to know the formula of expected value, to find the mean, and the variance, if they have. Cauchy doesn't have one, so. And that's it for chapter 5. Now when we come back, we're going to talk about a bivariate random variable, joint distributions, covariance, correlation, independent random variables, sums of independent random variables, convolutions, functions of random variables, change of variables formula. We did a change of variable formulas in vector calculus. Then we're going to talk about limit theorem, Markov's, and Chebyshev inequalities. Okay, chain of bonds, law of large numbers. Law of large numbers is regarding the probability type. We have experimental probability, we have theoretical probability, we have what's another probability I forgot. So the law of large numbers is saying if you experiment enough times and your true probability, all those three probabilities will coincide with theoretical probability. And that guarantees us, when we do calculations, we can ignore experimental probability and the other probability, and we can use theoretical probability. And also statement of central limit theorem, I just mentioned. Central limit theorem says, if certain conditions is satisfied, which is very easy conditions to satisfy, and every probability distribution can be approximated by normal distribution. That pushes normal distribution to the throne of the king. And then we finish. And then we finish about this course. All right. Okay. And anyone has any questions? Okay, if no one has any questions, go ahead, study, enjoy your spring break. Catherine is asking, okay, let me stop